Hi everyone, I'm very glad to be here. So I will present you some work that I do with my supervisor, Sebastian Deavo. And in my talk, you will have a lot of figures and some sentences, basically. Okay, so that's the outline of the talk. Black holes are about quantum information. So I will start with an introduction on the controversy that you have with the use of information to study black holes and in fundamental physics in general. So I will present different complaints that you can find in the literature. And this will highlight the fact that if you want to use the notion of information, you need to be careful. Then we turn to our case study, which is the Hayden and Preskill model. Basically, they model black hole by what is called a quantum subwidth. And the idea there is that you consider that the black hole is doing a type of quantum computation in which information is processed but not destroyed. And then when you do that, you can see black holes, you can see the role in a communication protocol. And in the third part, we turn to the role played by quantum information theory. And so the idea is that when you think about the information theoretic abilities that black holes have, you can learn something about them. Okay, and then I will conclude. So let's start with the controversy. So it all starts with the Beacon-Stein-Hawking entropy. And as the presentation of Eric Curry has just made very clear, yeah, it's a sack of shit. what you said. Okay, we don't know exactly how to interpret this relation. There are different routes that you can do to motivate the thermodynamical origin of that relation. One of them is to use statistical mechanics, so behavior of a large number of microscopic degrees of freedom, together with some notion of information theory to relate the statistical notion of entropy to the area of the black hole. This was in particular done by Beacon-Stein back in the days. And so the idea for Beacon-Stein is that when a particle falls into a black hole, an observer looking at the black hole is losing information about that particle. And so the area of the black hole increases as to reflect the increasing the ignorance of that observer. So this has been highly criticized in the philosophy literature, mainly because facts about the black hole microstate, they should not depend on the information we as observer have about them, basically. But anyway, on the other hand, David Wallace has made the case that modern development really show that you can make the case for the thermodynamic origin of the entropy without ever mentioning the word information, basically. So I guess that you will disagree with Wallace about the fact that we can make the case for black hole thermodynamics, but some philosopher out there thinks that there is strong evidence now. And we mentioned that a bit later. So apart from some objection into using the notion of information to establish the thermodynamic origin of the entropy, there are further skepticism. One of them is by Christian Aude. On the basis of Shannon's mathematical theory of communication, he says that to be able to talk about information, a communication system needs to be present. So you need a communication system to be in place to be able to talk about information. And this communication system has an inherent minimal level of complexity. In particular, it is composed of an information source producing the information, supposed to be this. And then that information, when suitably encoded, it is transmitted through a communication channel. Okay, so you have the source, you have the communication channel, and Woodrick is basically saying that black holes, as they are described by general relativity, they cannot achieve the component of the communication system. So the condition to be able to talk about information are not met, basically. Other skepticism, and maybe a deeper one, is by Christopher Timson. So he critiques the famous slogan of Wheeler's, "Eat from bits." Because for Timson, there is a distinction between the pieces of information, which are abstracta, and their concrete realization in the world. And slogans like "Eat from bits," what they're doing basically is replacing the material component of the world, like field or particle, with an immaterial basis of information. For Simpson, you should not be able to do that. You always have to instantiate your information, your piece of information into something concrete. So fundamental physics cannot dispense with the material yet, basically. Okay, so then the question arises, what is the role that the concept of information can play in fundamental physics, and of relevance for today's workshop? What role does it play in the study of black hole? And Simpson, as a conclusion of his book on quantum information theory, also provides valuable guidance for that. He says that information theory should not be thought about as a theory that introduced a new thing into the world whose behavior you need to describe. The success of this theory is rather in the introduction of an alternative framework of inquiry. And in that alternative framework of inquiry, new questions can be asked, and you can also develop tools to answer them. But this framework of inquiry needs to be used with care, with some precaution, only in situations where a communication system is in place and without dispensing with reality. Once with these precautions, then studying the information carrying, storing, and processing abilities of physical systems can be a fruitful enterprise. And today I want to show you how this has been done in the model of Aude and Corbeel. This has been done for black holes, and in particular, this model implements Simpson's proposal particularly well. Okay, so that was the introduction. Now we go into the details of the Aude and Corbeel model. And this model is based on a central assumption that's that hypothesis is central if you want black hole to be suitable for such a information theoretic analysis. This hypothesis is called the central dogma. So it states the following: as seen from the outside, a black hole can be described by a quantum system with A/4G degrees of freedom, and this quantum system evolves unitarily under time evolution. The idea there is that you put the black hole in its atmosphere in a box, and you can interact with that box. You can send signal, you can receive signal from that box, and you will never be able to tell if the quantum system in that box is a black hole. What is important is that it's really a picture of the black hole from the outside. So from the outside, the black hole just appears as an ordinary quantum system. Great deal of theoretical evidence for the central dogma, so divided in two parts. One is the fact that black holes are thermodynamical objects, and so you have those degrees of freedom in the first place. So those are the modern development that Wallace uses to make the case for that. And then a second piece of evidence is the fact that black hole evaporation turns out to be consistent with unitary evolution. So those are even more modern development in physics. And basically, what those calculations show is that Einstein, Hawking, did not consider some small correction to the entropy, and those corrections to the entropy, despite being small, they really change the picture of black hole evaporation, and they make it unitary. So there is still a great deal of philosophical analysis that is needed to unpack those results, I think. But as a start, you can have a look at the paper of Chinti and Sankyun.
Sorry, can I ask? It's just a quick question about, because I think I know all the bottom paper,
yeah.
And these are about like solving the information paradox in a way consistent with unitarity.
Yes.
I would argue that this is not a proof of unitarity or evidence for unitarity, but it's perhaps a way of solving the information paradox with assuming unitarity, right? Is there some more evidence in the first paper that I don't actually know?
I'm not sure I get your complaint.
Well, my complaint is that I don't think there's actual evidence for unitarity. It's just you can still have unitarity and have some evidence for solution for the information paradox, right? Is that what you?
Yeah, I think so. Like we don't need more basically than this to have the central dogma from the outside. We need black hole to evolve unitarily.
Yeah, but it's not direct evidence for unitarity. That's my complaint.
Okay, yeah, in the sense that it's in the specific setting of black hole evaporation, and it's the only place where you can apply this formula. In that sense.
Yeah, in the sense of why should a black hole be a unitary system, like directly? And I don't think there's evidence for that. It's sort of more like an axiom, right?
Yeah. Yeah, exactly. It's just that if you, so unitarity is one of the axiom. And instead of saving the working picture, you choose the other one when unitarity is an axiom. So I completely agree. It's not a direct. Okay, I can see that. Okay, so the central dogma in this presentation is a working hypothesis. So we are accepting it in a way, and it gives important aspects. So the central dogma is important for us for two reasons, because the aspect given by this external picture is the fact that the black hole is composed of a finite number of degrees of freedom, and the fact that the black hole's dynamic is unitary. And when you have those two aspects, basically, you can start to see that black hole then, as other thermal systems, they're going to process information without destroying it. So the central dogma is actually suggesting that black hole process and don't destroy this information. But the process of information by quantum system can be represented with quantum circuits. Okay, so quantum circuits, they are representation of the change that occur to the quantum state of the quantum system. And it's nice because we can easily represent them on paper with a few lines and boxes. So you basically start, so the lines are your qubits, and they start in a specific state. And then the boxes that you see here, they're supposed to represent a simple unitary operation gates on the qubit. And those gates, they change progressively the state in which the qubit started. So you can also see this as that sequence of gates is generating a unitary, and you apply that unitary on your initial state to produce another one. Two essential components in this quantum circuit, we have the fact that we have a finite number of qubits, and the fact that the set of gates is basically generating a unitary. But those were the two essential components given by the central dogma, if you remember. The central dogma talked about a finite number of degrees of freedom. We don't say anything about their nature, but we can consider that they are the qubits on which the gates act. And the second point is that the black hole dynamic is unitary, so we might generate it with a sequence of gates. So the central dogma is basically the central assumption that allows us to represent with quantum circuits how black holes process information. And that's basically the idea with the Aude and Corbeel model, the Aude and Corbeel protocol. So now that we can represent how black holes process information with quantum circuit, we will be able to make very clear what is the role they play in a communication protocol. So we consider the protocol designed by Aude and Corbeel. The two main protagonists are Alice and Bob. Alice writes her secret in a diary, and she throws the diary into the black hole. The black hole then evaporates, loses mass, and the information about the diary gets encoded in the radiation. Bob has access to the radiation, and he would like to decode the secrets from the radiation. With a quantum circuit, it looks like that. So the red arrow is the information is that in Alice's diary is supposed to be that quantum state. And that quantum state falls into a black hole and gets encoded in a larger number of degrees of freedom among the black hole degrees of freedom. And then new Hawking radiation are released, and there is the remaining black hole activity. And the blue system represents what Bob has access to do the decoding. Of course, the quantum circuits, this model needs to be further specified, and you want the characteristic of that model to really represent the characteristic of the target you're trying to represent with that model. And black holes are still mysterious. We don't know everything about them. So you will have to make some assumptions in the characteristic that you choose to represent in the model. But those assumptions, if you want, they're not as important as the central dogma. The main assumption for this talk is really the central dogma, because with the central dogma, you can start thinking of black holes as playing a role in a communication protocol. So I will not discuss those one now. And now I need to give you a slide more detail into this model so that you will understand what new insight we can gain from it. So the type of black hole in which Alice shows her diary, it's an old black hole. An old black hole that has been evaporating for a long time and that is actually now past half the evaporation point. This means that all the qubits in the black hole are entangled with the radiation already emitted. And we imagine that Bob has been collecting those radiation since the beginning. So since the black hole was formed, Bob was able to collect those radiation in a quantum memory. And so when he applies his decoding operation, he does so using the entanglement he shares with the black hole and using the information, the new information released in the radiation. He applies this unitary, he is able to recover the state on his subsystem. Another important point is the fact that the non-local mixing character of this unitary. So we believe that even if the information is not destroyed by the black hole still hide information pretty well. This means that when you throw information into a black hole, it's going to get encoded in the structure of entanglement of a larger system. So you throw the information, the qubits interact, entanglements form among the different components, and now you don't have your information on a single qubit line, but more spread out among all the degrees of freedom of the black hole. So from the communication perspective, the diary falls into the black hole. Then you have the black hole degrees of freedom. And then the black hole only releases some degrees of freedom to Bob. There is a black hole remaining at the end. So only some of the degrees of freedom are released in the radiation. In quantum information theory, you call that a quantum erasure channel, because basically you lose access to a subpart of the system. So Bob don't have access to the full system to perform his decoding operation. That's called the quantum erasure channel. Okay, so now we have the details of the model. What's the role played by quantum information theory? And we're going to see that they use basically the tools from quantum information theory to get insight on how you can, how a fixed amount of quantum information can escape. In particular, what are the escaping mechanisms that allows that information to go out? And their analysis relates that entanglement is used in two interesting ways. The first way in which entanglement is used is to protect the information. Because I told you that we have that non-local encoding, basically, that spread the information among all degrees of freedom. So that when you lose access to a separate part of them, you can actually still recover the information from the remaining one. So that unitary that was supposed to conceal the information pretty well also protects the information against the effect of erasure. So that's one way, quantum error correction for those who are familiar with the term, in which you can use entanglement. Another way in which entanglement is used is actually to assist the transmission. So this is more using entanglement as a resource, very common also in quantum info protocols, because remember that this is an old black hole that is entangled with this early radiation. And Bob can actually use that existing supply of entanglement to perform his decoding operation. So entanglement is used as a resource. Okay, so to the question, how can information escape from an evaporating black hole? Eden and Press could use the tools of quantum information theory to suggest that to highlight the importance of entanglement in two ways: to protect the information and to transmit, to help its transmission. And I want you to notice that this framework was actually used with precaution, because a communication system was in place. It was the black hole between Alice and Bob, acting as a quantum erasure channel. And also we didn't dispense with reality, because this is at the end just a model of a black hole, a model of a target that is supposed to be there in the world. So as a conclusion, I want to make clear what we intend with this slogan: black holes are about quantum information. This slogan views quantum information theory as providing intuition and analytical tools that are relevant to fundamental physics. So the idea is simply that you can learn something new about black holes by reflecting on the information theoretic abilities they have. And this approach shows in particular that black hole has to do with quantum information because they basically enable its transmission. Thank you.